Good morning, everyone. We are very pleased to welcome you at the closing seminar of the LIFE Vacuums project. My name is Stevie Swedde. I work for Flanders Environment Agency and I will be your host today. Before we get started, I would like to share some practical information about the event today. Now, first of all, what is on the program? Well, we are here for the closing seminar of the LIFE Vacuums project. This is a project where 18 low-cost air quality sensors for PM, NO2 and O3 were tested, and some advice and recommendations on how to use them were made. Now, the program is going to be in two parts. First part is the results of the lab and field test with the possibility for a Q&A. And the second part is the launch of the guidelines on the sensor usage with, again, the possibility to ask some questions. Now, about the questions, you're very much invited to do so and by using the chat function. And you can see on the probably the right hand corner, right above, and you can see a little bubble with a question mark, and there you can ask or write your questions down. Please be aware that if you do so, your questions are anonymous. So it is very much recommended to also include your name or your organization together with the person to which your question is addressed. Now, also remember that some of the questions, and not all of them, we will be in the possibility to actually present. So if we have too many questions, we will probably address some of them after the event on email. Okay, now there's also some other important remark is that the session is going to be recorded. So the advantage of that is that it can be watched again on the Vacuums website. So we're going to start with the first part of the session, and it's going to start with an introduction of our project coordinator, Ms. Evelyn Elst.
Good morning, I'm Evelyn and I'm the coordinator of the LIFE Vacuums project. In this presentation, I will give you a short overview of our project. LIFE Vacuums is a project funded by the EU LIFE program. Vacuums stands for various assessments of air quality measurement methods and their policy support. So in short, we tested 18 low-cost air quality sensors and we aim to give advice on how to use them. The project was done by three partners: the Flanders Environment Agency, the National Institute for Public Health and the Environment, and the Netherlands Organization for Applied Scientific Research. We did this project because we want to support citizen science. To do so, we have to be able to give advice on the use of low-cost air quality sensors. So we really need to know the performance of these sensors. On this slide, I will give you an overview of our projects. As a first step, we made an inventory of the initiatives and projects with low-cost air quality sensors that were done so far. From their lessons learned, we were able to select 18 sensors we could test in the Vacuums project. We selected 8 PM sensors, 5 NO2 sensors and 5 O3 sensors. But before we could start testing their performance, we had to make a test protocol and we had to find out how to assemble and program these sensors. Then the real tests could start. First we did a lab experiment and then we did a field experiment next to the reference measurement station in Antwerp. During these performance tests, we had special attention for the data management, since these low-cost air quality sensors can give a lot of data. After the results of the performance tests were available, we made guidelines and recommendations on how to use these sensors. Besides the guidelines, we also provide a data portal where the data from the low-cost air quality sensors can be compared with the data from the reference measurement station. So, this was a short overview of our project. In the next presentations, my colleagues will present you the results of both the lab and the field tests.
Hello, I'm Danielle from Dinter. I work at TNO in the Netherlands. We did the lab testing of the particulate matter sensors for vacuums. I did this together with my colleague Marcus Blom So I will show you, first of all, the lab setup. You can see here a picture of our exposure box, which we built with the vacuum sensor inside. We tested different temperature and relative humidity settings, which was 15, 25 and 35 degrees Celsius, and relative humidity was 20, 50 and 80%. We generated aerosols using Pallas RBG 1000. As a reference measurements, we used the FIDAS 200S from Pallas. Since the box was relatively small, we could only tensor a certain amount of sensors together at once. So that's why we performed the test in 2 batches at the end of 2018. So here you see some of the settings we tested in batch 1. So you can see the PM2.5 concentration in blue and the temperature and relative humidity settings. And as you can already see, the PM2.5 concentration values were relatively high, up to 150, 200 micrograms per meter. That's higher than we would expect in nature in the Netherlands. We were unfortunately unable to lower these. But this we have to keep in mind when we look at the results. So these are the sensors we tested, the Nova Fitness, 2 Shinyais, but the PPD42 was not working, 3 Honeywells, the Dylos, of which only 2 out of the 3 were working, the Plant Tower, the Winson. Then we also tested the AlphaSense OPC N2, but unfortunately this malfunction, so I have no result to show you on this one. So how did we evaluate the sensors? First of all, we looked at the data availability, so which percentage of the data was captured. Second of all, we looked at the linearity, so how well does the shape compare to that of the reference measures. We tested this during a ramping experiment, where the concentrations were varying, giving same temperature relative humidity settings. Then we tested the accuracy, so this shows how accurate the sensor. We were able to measure the correct PM concentration. So when it's 100%, it's exactly the same as the reference. Lower than 100 gives an underestimation of the sensor, and over 100 is an overestimation. Lastly, we looked at the sensitivity to temperature and relative humidity. And we quantitatively looked at that by color coding some scatter plots. So let's first look at the data availability. What you can see here, the data availability is very high for all the sensors, for almost all the sensors, above 95%. There were 2 sensors where it was a bit lower. The Nova Fitness only had 46%, so almost half of the data was collected. And the Shinyai PPD60, it was 87%, so just below 90%. So, but overall quite good. Then we tested the linearity, as I said, during our ramping experiment. You can see the PM concentrations for batch 1 here, but it's similar for batch 2. And you can see that the PM concentration increases from 0, and for PM1 it goes up to 15 micrograms per square meter. For PM2.5, a bit higher, 80. And for PM10, you see we have a very high concentration, up to 800. This means that mainly the coarser particles are generated during our experiment. That's good to keep in mind. Well, when we look at the results, so we made scatter plots with 10 minutes data, and we then made a linear fit, which you can here see an example of. And for that, we calculated the slope and R squared. So here you can see the overall results for both PM2.5 and PM10. Let's first take a look at the R squared values. For PM2.5, you see that in general it's very high for most sensors, above 0.9 for almost all sensors. The exception is the Winson. There it's a bit lower. 2 of the sensors it's around 0.6, and for 1 it's almost 0.9, but not quite. Then for PM10, you see the R squared values are in general a bit lower. Still fairly high for quite some sensors, so the Honeywell, Dylos and Nova Fitness do well. And the Plant Tower it's a bit less, it's 0.8, and for the Winston it's even less, 0.5, and one does a bit better, 0.76. I won't go into the slope now because those are also reflected in the accuracy already. Here you can see the overall result of the accuracy for the different sensors. And as I mentioned before, ideally you would want it to be 100%. That means it's accurate. You can see for PM2.5 that there's an underestimation for all the sensors. The dye loss seems to be most comparable with an accuracy of almost 90%. And then some other sensors, yeah, it's doing a reasonable job, but not that well. 50% for the Honeywell. The Senior PPD 60, it's a bit higher, but keep in mind we calibrated during the ramping experiments, so it's calibrated with this dust. For PM10, you really see that the accuracy drops quite dramatically for all the sensors. For the dye loss, it's still the best, 43 and 46, but for the others, it's below 15%. So it really gives a high underestimation. Then lastly, we look at the sensitivity of temperature and humidity. You can here see some color plots. Color coded with relative humidity on the left and temperature on the right, and here we simply look by eye whether a sensor was sensitive. And for example, you can see here the third sensor seems to be sensitive to temperature changes, with mainly scattering at a certain temperature range. So this I made an overall results table, which you can see over here. What you can basically see, that sensitivity to temperature, some have some sensitivity, but it doesn't seem to be too much. Only the dye loss is moderately sensitive to temperature, and then the plant tower 1 is sensitive for PM1 at least. For relative humidity, the Honeywell shows most sensitivity to the relative humidity. Nova Fitness has some, but for the others it's relatively low, I would say. So then I can go to the overall conclusions. Well, as I said, the availability is very good for almost all sensors except one Nova Fitness, and one Signia is also slightly lower than 90%. Linearity, also overall reasonably good, we would say. Only the plant tower is less good for PM10, and also the Winston is not so good overall, both for PM2.5 and PM10. The accuracy, as I told you, it's overall relatively low, especially for PM10. Best results are there achieved by the dye loss. Sensitivity to temperature and humidity, overall we thought they were not very sensitive, but some showed some sensitivity, mainly the Honeywell to humidity. So which lessons did we learn? Well, first of all, it's very difficult to generate constant PM values in the lab, and also the PM values that you would more or less want. So we had a bit higher values than we would like. Next to that, the calibration out of the box by the manufacturer seemed to not be up to standard, at least for these relatively high PM values that we tested it for, because we saw underestimations. And these were mainly present in PM10, and that brings me to the last point, that for coarser dust, so that between 2.5 and 10 micrometers, the sensors seem to have more problems measuring those. And therefore we see a higher underestimation and also more R squared for PM10 compared to PM2.5 values. So those were our main findings. If you want more information, look at our website or ask me questions. Thank you.
I'm Jordi Verkotteren, and I've been working for VMM for over 15 years now. My main expertise is measuring and characterization of particulate matter. Within vacuums, my main focus was the PM data, so that's data validation, data analysis, and data reporting. The working principle of a PM sensor is quite simple. Particles are drawn into the sensor, they pass a light source, and light is scattered towards a detector. More particles in the sensor means more light onto the detector. Data validation is a process where we decide whether data is good or not. When you're working with low-cost sensors, you often find data that's strange or just impossible. Here are some examples of data that didn't survive the validation process. The first one shows a peak of a single sensor. That's not impossible, but when it only happens to one of the 5 units, it's probably something going wrong with a single sensor. Here's another case where one sensor gave a spike that was always on the hour or half hour. That's probably some sort of electronic interference, but we didn't find out what it was. Of course, it's important to know how often this happens. You don't want a sensor with crazy stuff happening all the time. And you also don't want to take these data points with you in the analysis, because a few outliers can really screw up the results. The report has 6 sensor chapters, where we look at time plots, correlations between sensor uncertainty, sensor reference ratio, and we also compare the sensor with the EU gravimetric reference. There is also a chapter where we investigate whether sensors behave different at different locations. That's something we looked at for one specific type of sensor, and it's got some pretty interesting results. Anyway, if you want to know what's in it, you'll have to read the report, or you can start by watching a 15-minute video elsewhere on the website. First of all, different types do give different results, and some sensors are clearly better than others. In general, the results for PM2.5 were good or reasonable. Sometimes sensors do need calibration, but that's something we can live with. The results for PM10, however, they were not so good, especially if you look at the coarse fraction alone. So that's the particles between 2.5 and 10 micrometers. All sensors we tested gave pretty bad results. Some even used a very basic algorithm that makes no sense at all. For example, the Honeywell, it just adds 1 microgram when PM2.5 is below 25, and it adds 2 microgram when it's above. So it's just making up a number. We noticed that other locations can be more challenging for sensors, especially places with a lot of vegetation where we see that the humidity is often higher. And high humidity makes particles grow by taking up water, and that makes sensors overestimate. We also noticed that the field results are quite different from the lab results, which just proves that it's hard to simulate real PM in the lab. So what are the most important conclusions out of this research? I think co-location of multiple units is a good idea to help you identify data that is just wrong. All sensors were bad at picking up PM4s, and it's impossible to put a single number on a sensor. It's like asking what's the best tool or what's the best software. I think it's also very important to communicate clearly what these sensors do and don't measure. And PM itself is complicated. There's a lot of chemistry involved, and the sensors don't actually measure the mass of PM itself, so that makes it even more complicated. You have to understand PM, and you have to understand the sensors. Sensors have no idea about the composition of PM, and the composition does play an important role in how the sensor reacts to the particles. And for certain applications, the best sensor might not be good enough. The thing I'm most proud of is the collaboration with different colleagues at VMM, at RIVM, and at TNO. From a scientific point of view, I think it's the focus on PM cores. That gives some new insights. So what would I like to try next? Well, probably further investigate how sensors can help people who suffer from wood smoke, to provide some sort of proof of the hinder. And maybe just for fun, put some sensors on a drone and do some 3D measurements and see what we can find.
So my name is Ernie Weijers. I work at RIVM, the National Institute for Health and the Environment, and I work in the field of air quality with a special focus on low-cost air quality sensors. So one of the actions in the vacuums project was testing gas sensors on their performance in the laboratory of RIVM. It was actually the first time that we did such a thing, and I have to say it was a rewarding experience. We learned a lot. In this speech, I will briefly tell you what we did, how we did it, and give 2 examples to demonstrate all this. First, the sensors. Here a list of systems that were selected at the start, and 5 units of each type were purchased and tested. They were made available by VMM. And then what did we do? we use the so-called exposure box. A photo of this is on the right. Inside the box you are able to change humidity, temperature and the presence of pollutants in a controlled manner. A reference instrument measured the gas concentration inside. Its inlet was positioned in the center and also temperature and humidity were registered. The box itself is large enough to contain all the systems, and the testing was then done in one cycle, so simultaneously for every sensor. One of the tests was a ramping experiment. We changed the concentration in the box every 2 hours, keeping temperature and relative humidity constant, and studied the response of the sensors. Here the result for the two NO2 sensors. The reading of the reference instrument is in red. Sensors have various colors, and as you can see, sensors react to changes in the concentrations rather well. They follow the reference rather well, but interesting is also to see that the concentrations as measured by the sensors always underestimate the reference signal. And this is especially apparent at the higher levels. Well, this was not unexpected. We already know this from tests in the field and other lab experiments, but it clearly demonstrates the need for a further calibration. Well, here was the second example. This was the alpha sense, and here we have the care clip, and both they react in the same manner. The second example, does a sensor measure other gases than the one that it is made for, is used for, the cross interference? Here we have two NO2 sensors. Sorry, we have 4 NO2 sensors, the alpha sense, care clip and 2 membrane pores. And again, we use here a ramping test with different levels of ozone while keeping the NO2 at the 0 level. Reference instruments are again in red. The dotted line is NO2 at a 0 level. It's here. And the dashed line denotes ozone with 2 step changes. And what is the result? Well, we see a different response for different sensors. Whereas alpha sense in green and care clip in blue remain at the 0 level, both membrane pores deviate and are influenced by the presence of ozone. The one sensor even more than the other. So, very briefly, 2 examples demonstrating the use of the exposure box and also demonstrating the work that we did in vacuums. We studied more properties and gave results in fact sheets per sensors, and also one summarizing results for all sensors. And here's then an example for NO2 demonstrating what we looked at more in the project. As you can see, several properties were studied: linearity, deviation from the reference, stability between sensor uncertainty, and the response to a change in relative humidity. We did something similar for the ozone sensors. Well, basically, this is what I'm going to tell in more detail in my talk, and you can also find these results in one of the vacuum reports. So this was the last sheet of my presentation, and I would like to thank you very much for your attention.
My name is David Roet and I work at the Flemish Environment Agency, mainly on topics related to air quality modeling, but I also like programming and playing around with data. In the Vacuums project, I mainly help with programming the ESPs and also with setting up and configuring data communication of the sensors. We will now show some of the main findings of the report for the low-cost nitrogen dioxide and ozone gas sensors. So, what is in the reports of the low-cost NO2 and ozone gas sensors? You will find a thorough comparison and statistical analysis of each sensor type and of the 5 individual sensors. We will address the following topics: validation and data coverage, how much sensor data is usable, calibration using orthogonal linear regression when there was a linear relationship, or different multiple linear regression models in other cases. Comparison of uncalibrated and calibrated sensor data with reference measurements. The influence of ambient conditions like relative humidity, temperature, and other interference. and we will show the R-square mean bias between sampler uncertainty and relative expanded uncertainty. So, what are some of the main results? First of all, there is quite a big difference in the results of the NO2 and ozone low-cost gas sensors. For NO2, 3 out of 5 sensor types showed no linear relationship with the reference measurements, resulting in scatter plots with blobs and whales. Another problem was the occurrence of negative values. Here you see some results for NO2 sensors. On the x-axis we have the NO2 concentration measured in the reference station. On the y-axis the concentration measured by the sensor. The black line shows a perfect one-on-one agreement. On the left you see that the AlphaSense and the Envea Care Clip show some kind of linear relationship, while on the right side the CityTech and the Membrapore show no obvious linear relationship. We see shapes like blobs and whales. One of the ozone sensor types, the Aeroqual SM50, performed very well straight out of the box, with an R-square of over 0.9. Here you see the results for the Aeroqual SM50 ozone sensor. On the x-axis is the ozone concentration measured in the reference station. On the y-axis, the concentration measured by the sensor. We see that there's a very good correlation and an R-square of over 0.9. For this sensor, no calibration was necessary. Multiple linear regression models with the interferent pollutants NO2 for ozone sensors and ozone for NO2 sensors, and ambient conditions like relative humidity and temperature are able to improve the results, the R-square. But underestimation, a negative bias, and between sensor variations remain. Each sensor has its own fit, making generalizations complicated. Here you see the results for the Membrapore C1 and also C20 NO2 sensor. At the top are the results of the uncalibrated signal. At the bottom, the results after applying multiple linear regression model. Before calibration, we see that scatter plots show a typical non-linear relationship, here in the shape of whales, and the R-squared is very low, below 0.05. Also, the distribution of the sensor to reference measurement ratio has a very skewed distribution. After applying the second multiple linear regression model, we see that the scatter plots, the R-squared rises, but still has an underestimation. The distribution is no longer skewed, but the multiple linear regression models depend on good quality meteorological data, temperature, relative humidity, and good measurements of the interferent ozone and NO2 in order to work well. However, degradation over time and limited lifetime remain important issues. Here you see the results for the Membrapore C20 NO2 sensor. First, a time plot at the beginning of the field campaign in 2019. At the bottom, in the end of the field campaign in 2020. Let's take a closer look at the behavior over time for VQL4, sensor number 4. At the start, there was more or less a constant offset for the sensor. But at the end of the field campaign, there were a lot of spikes and strange behavior. There was a clear degradation of the sensor over time. So, what are some of the conclusions? There are big differences in out-of-the-box performances. Almost all NO2 sensors need a correction to become useful. For ozone sensors, the situation is better. The majority is usable. Calibration with a reference monitor is useful, but also is accounting for interfering gases. The extended multiple linear regression model, MLR2, is able to improve the raw measurements. Degradation over time remains an important issue for all of these sensors.
So, I have to admit that some of the results that were broadcasted were actually quite fascinating. Before we move on to the Q&A session, I would like to draw some attention to the LIFE Vacuums website, which is vacuums.eu. Now you see that many of the speakers already referred to it, and it is there where you can find all the detailed reports and even some more extensive videos on the project results. Okay, so now I would like to introduce you to our expert panel for the Q&A. We have here with us we have Danielle from TNO, Danielle van Dinter. We also have Jordi Verkauteren from Flanders Environment Agency. We have Ernie Weijers from the RIVM and David Roet also from Flanders Environment Agency. Now, these were the same people as were in the presentations. Now, so let's move on to one of the questions. Now, I already mentioned it. We'll try to do our best to address all of them, but sometimes it might be that we run out of time, or that the answer would be maybe too elaborate or too expensive. And then, therefore, if you would be able to keep adding your name and to the question, we will try and do our best to provide you with a written reply to all of your questions. Okay, but there's one which we will, or a few at least, which we will address now already specifically. And I have one for Danielle. Danielle, we have a question from Michelle from the JRC. And Michelle's question is, did you calibrate the sensors yourself, or were they calibrated by the manufacturers?
Yes, thanks for the question. I hope I'm live now and that you can hear me.
Yes.
So what we did within Vacuums, we decided to follow the protocol which was given by the manufacturers of the sensors, which meant for the PM sensors that most of them were already calibrated, which means we would take them out of the box and use the calibration given by the manufacturer. But this was not the case for the Xinyai. So this one we had to calibrate ourselves, which we did in the lab and in the field, and then we use the calibration function given by the manufacturer.
Yes. All right. Thank you very much. Well, Michelle, I hope this is a reply to her question. I also have another question, which is for Jordi. Jordi, we have a question from Marita Voogd, and she asked, can you explain why the PM sensors in the lab tests were not influenced much by relative humidity, whereas in the field they were? Jordi, can you maybe elaborate a little bit on this?
Okay, very good question, by the way, from Marita. It's something that we also noticed, and the reason is probably that in the lab test, the PM that was used was Arizona test dust, so that's a desert sort of desert dust, which is much less hygroscopic. So if you're going to expose those to higher humidity, those particles are hardly going to grow. However, if you go to real life, as probably most of the experts know, a lot of the PM consists of ammonium salts, other type of particles, which do grow a lot more when humidity increases. So that's probably the reason. It's a difference in composition. And as I mentioned in the video, the composition really matters, and it changes the way particles grow, and hence it also influences the way the sensors will react to particles and to the different influence of relative humidity.
Yes. All right. Thank you, Jordi. Maybe a question for all of you, but maybe specifically, well, Ernie, maybe if you can say something. Do you have some advice for citizen scientists on which sensors they should buy?
Well, based on the lab results that we received, I should say that there is not one sensor that is acting like the ideal sensor. For a number of properties, you can see that the alpha sense is performing perhaps a little bit better than the other sensors in case of NO2. But overall, there is no real one sensor that you should select, that you can select, being the best. So my advice is to buy a number of sensors and see how this works out in practice in the field.
Yes. All right. Thank you very much. Maybe maybe some of the other panel members can complement something on that. David, do you have an advice on for citizen scientists on which sensor they should buy?
Well, I think it all depends, first of all, on what you want to measure. If you want to measure gases or PM, I think for PM the situation is a bit better or different than for gases. So I think if you should start, maybe it's easier to start with the PM sensors and later go to the gas sensors, although both have their own problems. But I think probably starting with the PM sensor is likely to be the best starting point.
Yes, I have also another question for you. Maybe the question came from John Saffel. Do you prefer the R2 or RMSE as a metric of sensor uncertainty? Because we frequently refer to the R2.
That's right. I think actually both metrics are important. Maybe in the presentations we gave, we put a bit more emphasis on the R squared, but both the R squared and RMSE are important metrics. So I wouldn't prefer one over the other. Just look at both of them together.
Yeah, all right. Danielle, I have another question that is there for you. A question from Martin. What was the RH range the sensors were tested?
Sorry, can you repeat it? I missed it, sorry.
What the RH range of the sensors was that were tested?
Oh, so we tested 20, 50 and 80%. I did it by head. I will double check in my presentation. One second. Yeah, 20, 50 and 80% indeed.
Yes. All right. Thank you very much. I'll have to see. I will actually. We still have a number of questions that actually came in, but that are maybe slightly more complicated and probably deserve a more elaborate response, specifically regarding some of the gas sensors, maybe, which we will address then at a later stage and by email. So if your question hasn't been addressed to at this point, I would like to thank you anyway, and we will make sure that you will receive a written reply on those questions. In the meanwhile, we also try referring to the reports which are on our website, and of course we will try to get back at you as soon as possible. But now at this point, I suggest we move on with the program. I would very much like to thank the experts in the panel. Thank you, Ernie. Thank you, Danielle. Thank you, Jordi. Thank you, David. And we will hope to see you again. They are also available for questions, and their email addresses are at some point in the website. So if you would have some specific questions that pop up later this afternoon or in the weekend, then please do not hesitate to look up and forward them your pressing issues. But now, okay, let's move on to the second part of the program. And the second part is more targeted around the guidelines. And we will start with an interview with Christophe Stroobans, who is the team leader of international projects on air quality within Flanders Environment Agency. And he will talk a little bit on the guidelines on air quality sensor usage. I would suggest that we could have a look at the interview.
Good morning. I'm Evelien and I'm the coordinator of the LIFE VAQUUMS-project. I sit here with Christophe Stroobans, who is the team leader of the international projects on air quality of the Flanders Environment Agency. Today we will talk about the lessons learned of the LIFE VAQUUMS-project and our recommendations on using low-cost air quality sensors in the future. So Christophe, how do you look back on the project?
Well, the project actually started off with a questionnaire. And we asked our participants on what type of sensor they planned on using or were using, the drivers, the reasons why they were using those sensors, and the problems they encountered. So if you use that as a point of reference, there were some things we noticed. For instance, our sensor selection actually covered about 90% of the sensors that were used by respondents, both citizens, local policymakers, environmental experts, and a lot. And often the sensors that were not covered in our selection were actually on the more expensive side, and were left out of scope for the VAQUUMS project, given our focus on use by citizens. So this is a good indication actually that our selection procedure was a valid approach. So I'm glad, because that was the starting point, obviously, for the project. Another thing we noticed is that many of the drivers actually involve using air quality sensors as a dialogue starter. So using them as an argument for local action, or just out of curiosity, or to learn kids about air quality. And that's something that we now take into account when we work with municipalities or when we advise citizens. So that's an interesting point where VAQUUMS brought us a step further. And then thirdly, something we noticed was that the problems that people encountered, the things that needed clarification were interference, longevity, stability of the sensors, variance in a single sensor type, comparability to reference monitoring. Those were all rather unclear and a sort of roadblock for using air quality sensors. And we actually faced similar challenges in the early stage of the project. We had questions like, how do you compare across studies? How do you interpret tests that have lasted only for 2 weeks or maybe a month, when your goal is actually using the sensor for 2 years or longer? And I think we were able to provide some decent answers with the Vacuums project to those questions. Our test was quite unprecedented in nature. Each sensor was co-located in 5-fold with reference equipment for a whole year. So we've been able to thoroughly look at these questions, look at interference over time, look at calibration stability of the sensor signals over time. Also compare lab and field results, which is often something difficult to interpret in literature as well. And I'm quite glad actually with looking back at the project with this unique achievement and this one-of-a-kind benchmark that we were able to set with the Vacuums project.
So in hindsight, have there been any missed opportunities?
We used an approach that closely resembles a citizen's approach, in particular regarding sensor construction, sensor calibration. And what we've noticed in our test results is that, in particular for gas sensors, these devices are too much of a challenge for such an approach. They often require complex calibration algorithms, and it's not feasible in this approach. That's something we might do differently if we were able to start over. But it also actually inspired an idea we had, an idea that was pitched to have an open challenge on sensor calibration, and that's something I would like to see us pick up in the future, in the afterlife of the project.
And how would such an open challenge look like?
That would probably use an online platform where we would try and involve citizens, anonymize the data, put it out there as an open data set, and challenge them to calibrate the data, for instance, based on the first month of measurements, and then validate it on the other 11 months, and that would provide an additional stimulus for citizens to get involved in the scientific side of air quality.
If the project would have had more time and resources, would you also have involved other stakeholders?
Yes, definitely. I'm pleased with how we were able to involve experts, both in the sensor selection and in an attempt we had at defining a sensor quality index. It also allowed us to build stronger cooperation with citizens and municipalities. And the project ultimately helped us build this hands-on roadmap for using air quality sensors in cities, for instance. But given more time or resources, as you asked, I would have enjoyed exploring further involvement of sensor developers, for instance. Right now it's limited to something we're able to do in part thanks to the project. A concept called Open Innovation Monitoring Stations, where we provide the opportunity to sensor developers to co-locate their equipment at a number of reference sites to improve their product. But I would have enjoyed delving further into that, perhaps challenging them also on the calibration part of the sensors. But it was out of scope in the project as it was now.
As is the case in most projects, not everything went according to plan. What would be the most important lessons learned? Yeah,
well, there's lessons learned on the scientific side. For instance, there were huge differences between sensors of a certain type, also between lab and field results. I mean, that's not really a surprise, but it's still amazing to see how big the differences can be. I think those elements have been highlighted as well in the videos we published on the sensor results. We also noticed that you always need a baseline calibration, not just for the gas sensors, which often require complex calibration, but also for the particulate matter sensors, for instance. other than the scientific side, I'm also remembering many practical issues we had when trying to get the sensors up and running and having them operational.
And in what way was this extra challenging, this practical side?
Well, in our setup, which was a citizen-based approach, we used only low-cost components, so low-cost sensor devices, low-cost microcontrollers, low-cost communication units. And I mean, adding 3 types of low-cost device results in a lot of compromise, and it was really difficult to get them up and running. We actually expected to find a lot of sketches, for instance, for Arduino and such things online. We thought they're probably all there, but often we found 3 different sketches and none of them worked. So I think ultimately it's actually it's a positive story. We now have the sketches. We will provide them as part of the vacuums output, and we hope to save time with anyone who wants to work with these sensors in the future, and we hope they can use our sketches for that.
Now that the project is coming to an end, what key aspects should we keep in mind?
Well, yeah, there's a number of things. One thing I think we did quite well was standardizing the tests. So we've drafted testing protocols that we've aligned also with ongoing work in European normalization working groups. So there's probably still work to be done there, but I think our testing protocols can be used there to work towards a common standard and more intercomparability across sensor tests. And something else we really need to keep going after the project is just testing the new sensors, new devices that are released to the market, but also explore new ways of calibrating or maintaining calibration on gas sensors, for instance, because results there are still difficult to interpret at times, and they show that simple calibration procedures are not really very easy to apply to the gas sensors.
Almost every year we notice an increase in requests from cities, citizen scientists, but also from private sector regarding to air quality sensors and sensor networks. How can the LIFE VAQUUMS project help in addressing those requests?
Well, one thing I'm thinking of is, I mentioned before, it's the open innovation monitoring sites. They allow us to help the private sector in developing a better product. We open up a number of monitoring sites, and we help sensor developers apply our standardized testing protocol to these comparisons, and they help them improve their product, start a dialogue on calibration, algorithms, improvement of algorithms, and those things. So that's one thing. Looking at citizens, obviously we now have an expanded evidence base. So we can refer to the test results to provide them insight into which device to use, but also the sketches, as I mentioned before, for building the sensors and getting them up and running. They're very valuable for us. I mean, it's part of the experience we gained, and it allows us now to provide very much more concrete advice to both citizens and citizens.
Let's talk more specifically about these cities and municipalities. Do you see opportunities making their adoption of these new technologies more easy?
Yes, definitely. I think from our experience with the cities and the municipalities in the VAQUUMS project, we've learned that it's often difficult for them to comprehend the scientific side. I mean, there's a lot of science involved, very extensive reports on test results. So we should really try and translate our results into a comprehensible set of recommendations. And our train of thoughts currently is actually to do something in analogy to the open data charter that we have in Flanders, for instance. So this open data charter is a set of principles backed by a number of cities in Flanders. in which they state that they will go about publishing their data in an open way by certain governing principles, for instance. And we would like to do something similarly for air quality sensors. So work together with the cities to develop a charter with a limited set of governing principles on how to go about implementing citywide sensor networks, for instance.
So what principles could be in such a charter on air quality sensors?
Yeah, well, obviously there's an important link there to our roadmap, for instance. It's about tailoring your approach to the budget you have, to the current state of art, to the goals you're setting, and being as specific as you can in that as well. So it's much more easy to use sensors for a very, very specific research question and use case in a limited area of the city, for instance, than trying to use sensors to address any number of goals throughout the city. So tailor your approach and also develop through experimentation. Start small, don't expect to roll out sensors across the city from the get-go. No, start small and build your sensor network through experimentation. Those are the main two principles coming from the roadmap, and then we would like to add, based on the lessons we learned and the things I've mentioned in this interview actually as well, encourage further sensor development through things like continued comparison with reference sites. As a city, if you want to purchase sensors, oblige the developers, the providers, perhaps through the tender, to compare them to a reference monitoring device in a standardized testing protocol. Use those sensors as much as you can alongside other methods to build best practices, because that's a thing we see that's missing. There's a lot of information on the scientific side, on the test results, and our expert workshop actually learned that there's not that much. It's not that easy to link the sensor quality or the performance and the test results to use cases. And we actually need more information, more best practices, more successful use cases. So whenever you can, try and include sensors in a monitoring campaign that also has reference methods, for instance. So those are the main principles we're thinking about. One other thing is don't do it alone. There's a lot of areas of expertise involved. There's data science, there's air quality, there's data communication, there's a smart city aspect, there's a citizen science aspect. So try and get all of those experts in those fields involved, and they will also help you specify the use cases.
I think this charter will be an added value as well for citizen scientists as for cities who want to start measuring air quality in a sensor network.
Yeah, I wholeheartedly agree. The principle of the charter would be that it allows, it's a signal actually that the cities that are backing the charter won't rush into things. They won't start using air quality sensors without thinking it through, without applying certain governing principles that try to ensure at least a minimum level of quality and maybe a minimal chance of success. So it's really a statement of determination of the cities to implement an air quality sensor network purposefully and with a clear goal in mind and a clear impact in the field.
Thank you, Christophe, for this very interesting interview.
You're very much welcome, Evelyn.
All right, thank you, Evelyn and Christophe, for this interview. In the meanwhile, we have been looking at all of your questions that came in, and we have to say that there is some work for us processing them. But if I am lucky, I am online with Christophe now, and we can look into some of the questions that came in. Christophe, I have a first question from you, which is coming from Hannah Rijn, and Hannah is asking if it's should we really use the sensors if there's a high probability of getting the wrong results? Wouldn't it be better to not measure instead? Christophe, do you have something to reply on the question of Hannah?
Yes, thank you, Hannah, for that question. It's a good one. We're also struggling with that from time to time. I think Jordi was going to weigh in as well right after, but from a usability perspective, there's always the minimum case where you work on sensibilization on air quality as a whole with citizens, but also on the difficulties of monitoring air quality. I mean, the fact that so many citizens are willing to monitor air quality and believe this can be done cheaply, that's an indicator that some sensibilization is required also on how low the concentrations actually are that we want to monitor, how difficult those things is. So sensibilization is always a basic thing that can be done. Obviously, you would prefer to do it with usable results at the end, because that will motivate the citizens. But looking at the problem from the other way around, even with a well-performing sensor, we've noticed in one of our workshops with European experts that it's not possible to say upfront that you will be able to measure the outcome you're looking for. For instance, if you want to evaluate the implementation of a measure, it might even be difficult with reference equipment. So we brought together a number of European experts and tried to devise some standard quality framework for specific use cases. And the end result was that it always depends on what happens in the field during the experiment. So you'll always need a degree of experimentation. There might be some minimum level we can build on, but even with a good sensor, you're unsure that your use case will be valid, which is why in our roadmap, I think it was at the end of the interview, I mentioned it as well. We recommend to build a sensor network or any kind of deployment based on experimentation and validation of whether you can actually use the sensor for a certain use case. But Jordi might have some things to add from his expert point of view as well.
Yeah, I guess it's a matter of what's wrong and what's not. Some sensors can be wrong at a certain moment and be right or less wrong at another moment. For example, for the PM sensor, I think it's very important to know what these sensors are picking up and what they're not picking up. Like we've seen both in the lab and in the field, that they're really bad at picking up PM cores. So you should know that these sensors are not very good if you want to start tracking, let's say, construction works, certain industrial activities, resuspension by road traffic. Your sensor is not going to pick up those. So you should be aware of that. However, we do know that most of the PM sensors, or basically all of the PM sensors, are pretty good at picking up wood smoke. So it's one of these things that there's no right or wrong. It's just that sensors are better for certain types of pollution. So it's always good to know, like if you don't see a high signal, well, that doesn't mean that there is no PM cores problem. But if you don't see anything, you can be pretty sure that, for example, there is no issue with wood smoke. So that's one of the things that we really want to focus on, like understand what these sensors are measuring and how they react and when they are wrong and when they are less wrong or pretty close to the reference situation. So it's always the same in science. Understand what you're doing. Basically, that's the main lesson, and understand what the sensors are doing.
Yes, all right. Thank you, Jordi and Christophe. Now, it's already mentioned a number of times that there is an emerging interest in these urban air quality networks. Christophe, maybe can you elaborate a little bit more on the roadmap that is developed for these networks?
Yes. So there's a separate video on that as well in the supporting videos section on the Vacuums website. But basically what we did is we were contacted by a number of municipalities in Flanders during the LIFE VAQUUMS project to help them in a project where they wanted to investigate the usability of more expensive air quality sensors in an urban sensor network. What we did there was we had a workshop organized by Board of Innovation, which is an innovation consultancy firm, and the Flanders Institute for Technological Development, VITO. And from that, we gathered an approach, a design thinking approach, in which cities first assess the needs they want to address. So who are you really doing this for? What do you want to achieve? Do you want to inform citizens on behavioral aspects? Do you want them to change their behavior, to reduce their exposure, to reduce their emissions? That's all different kinds of endpoints. You might also have some internal stakeholders that you want to support, like your environmental managers in evaluating measures or acting on calamities. So there's many potential use cases. So the first step, assess the needs of all the stakeholders you want to help, and then select and prioritize them and see on which ones you want to act. That's the first step. Second step in the roadmap is then thinking of solutions. So brainstorming, what can we do? Do we really need a sensor network, or can we do this in another way? Can we use passive samplers? Is this something that can be derived from models, perhaps? I mean, that's a really important step to also question your often initial intent. We need an air quality sensor network. Is it really needed for the cases you identified? So that's the envisaging solution step, as we called it. And then the final part of the roadmap is actually on developing an implementation plan based on experimentation. So that's what I mentioned with during the initial question already. I mean, we see that you always have to have some kind of degree of experimentation, and we outline how you can implement that based on insights in user needs and the solutions you envisage. So that's in a nutshell what that roadmap is about. But I invite everyone to have a look at it at the supporting video and the roadmap document as well, which is under the deliverables section on the website.
Yes, thank you, Christophe. I don't know if we still have David present here from the panel, because there's a question from Bino. Bino is asking whether the sketches that were mentioned, will they be posted on a GitHub repository for interested citizens, so they can also comment, join the discussion, or contribute to the process?
Okay, thanks for the interesting question. I already wrote a slide answer in the chat. So actually there are two types of sketches. We have the sketches on the Arduino that are controlling and reading out the hardware of the sensors themselves. And we also have another firmware, what we call, so the software that is on the ESP, which is sending the data over Wi-Fi to our data points. So yeah, indeed, we also use a lot of public code and different repositories, especially for the firmware. So we are looking at how we can best share all of the available code and sketches with you, likely on the GitHub, and we will share the link then on the Vacuums project page.
All right, thank you very much, David. Maybe I'm just looking into the time, and there are some additional questions came in from the first session on the sensors and the field and lab test. Maybe I'm looking to Christophe. He can maybe also pick up some of them. There was a specific question from Walter, for example. Is there a reason that the Sensirium SPS 30 was not tested?
Yes. Well, you should bear in mind that the project started a couple of years ago. We did an inventory based on a literature survey of what is available and what sensors scored above a certain threshold. I think this is somewhere among the resources on the website as well. And then we asked experts to validate an initial list of sensors we targeted, and they said, okay, some were obsolete, some had to be added. And the Sensirium was just not part of that list at that time. Maybe it got some attention right after, but we were unable to pick it up in the months after. So that's the reason. It's not that we believe in the sensor, but it was not picked up in literature survey or by our European expert panel that advises on the matter.
All right. Many thanks, Christophe. There's also another slightly related question. Would you be interested in also testing a sensor for black carbon?
Yes, very much. To our knowledge, there isn't one. So I'm very keen on hearing from Hannah what device she's thinking about. We currently sometimes use the italometer, the HA51s, and they're quite reliable, but they're quite expensive as well. So we wouldn't consider them low-cost sensors. But it would be useful addition, we believe, because we see many questions by citizens that could be answered in part by monitoring black carbon. Also because of the very local or more local variation of that pollutant compared to other particulate matter fractions, for instance. Don't know if any of the other experts want to weigh in. Not seeing any hands in the back end, so it's okay, Steve.
It's okay. I remember that you're interested if there would be a very good option to do so. Maybe the next question is actually also a very good one. It's a question from Marita. How would you cope with private companies that want to test their sensor at reference stations? Would you request open data, or how would we consider working with black boxes? Like, for example, not knowing the types of sensors and calibration details. Christophe, maybe you can also say something about that. Would you be open to do that?
Yeah, thanks for that question. Yeah, we're actually doing that. So we have the concept of the open innovation monitoring stations, and we have a procedure that's written in our quality assurance system at VMM, which I could actually share. It's in Dutch, but I know from Marita that that's okay. Which describes how we handle those things. And in principle, what we ask is that we can see the data, we can do some comparisons ourselves. We don't demand that we can actually share that data again afterwards, but up until now, in my experience, we haven't had any problems with that. Actually, the idea behind it is that we gain some knowledge on sensors available and what their performance is, and that the developer gains some insights from our experts on which specific circumstances lead to failures or bad results. But I can definitely share the procedure with Marita if you want to. We actually have a starting and a closing meeting to address those things in principle.
All right. Many thanks, Christophe. And that brings us. There's still a number of open questions, but I was very. I was asked to repeat again that we will try to address them as detailed as possible, because some of them just require a little more attention. But apart from that, we are sort of nearing the end of this event, and I would like to share some closing thoughts with you. Yes, some take-home messages about the most important items which we discussed today. What are the take-home messages? What has Life Vacuums learned as well? It is important to gather information about the pollutant that you are measuring and try to understand on how the sensor is working. And this will help us to interpret your measurements. Another important aspect is that the laboratory tests, they are useful to gather information about the characteristics of your sensor. But the field tests, on the other hand, are needed to learn about the performance of the sensor in more natural conditions. That's also a very important thing which we learned. Another part is also that some of the PM sensors, they give promising results in the field tests, but additional development is still going to be needed to improve the quality of the gas sensors. Another element is that there's a need for use co-location and the calibration to improve the sensor results. But you can make sure you always know that the corrections which are actually being doing. So you also should need to monitor that. And finally, maybe also a very important take-home message for all of you is that before you start measuring, just really think your experiment through. Use the roadmap that is built for a strong implementation plan for urban air quality sensors. I think one of the most important aspects is that the vacuums show that it is possible, but you have to be very well prepared for it, and that a lot of the tools that were actually made and a lot of the work that has been done by the partners in this project will be able to help you achieve your goal in this regard. We're nearing the end of this project, of this event. I would like to thank you all for contributing. I would like to thank the experts and the people. I would specifically like to thank Evelyn. Evelyn, our project coordinator, has invested a really big effort in trying to make this event a success. Apart from that, she's not alone. We also have a very good communications team who is trying to make sure that in these challenging times we still have a very nice online alternative to do that. Of course, we would love to see you in real life once again, and maybe we can do so. Maybe we can do that in 2 or 3 years from now. We can actually show you some of the sensors that we were used, and then we can do it. Can do this again, and we can do it bigger and better, and we will try to make sure that we can make the best out of it, and to keep working on this process, which is a very promising trajectory for the future, I think. So thanks a lot for joining us. Please do check out all the presentations, check out the videos, check out the reports at vacuums.eu, and we look forward on seeing and speaking and interacting with you again in the near future. Thanks a lot and have a good Friday.